Morning, guys.
So I think we got all the documents. We got the committee here.
My
Should I wait any longer, Drew, Susie, or
you
got ready to
Colonel?
I think we're good to go.
good to go?
Colonel,
Okay, awesome.
he's doing
Welcome
biochemistry on hematology.
Trevor's qualifying exam. I think everybody here knows Trevor, so I don't have to do too much of an introduction. Welcome. It's so nice to have you here.
Nice to meet you.
Welcome back.
Well, so Trevor joined our program with a bachelor's from West Point, and then he actually earned his master's across the street in chemical engineering. Has a ton of other training, which I cannot even begin to understand, but makes me feel safe. And now we're really fortunate to have him in our program as a PhD graduate student. So
Thank you, Susie. All right, so today I'm going to be talking about two different topics. First is going to be a broad overview of my research over the last 7 months, and then we'll transition into a grant proposal that I developed in fulfillment of the qualification requirements for BIOEN. But before I do that, I just wanted to especially thank the committee, Colonel James for flying all the way over from West Point to be here, and then all of you for agreeing to take time out of your busy schedules and looking at all of the wonderful writing that I did and listening to this. So we'll go ahead and get started with strengthening the clot, nonlinear rheology meets trauma medicine. Susie kind of alluded to it already. Sorry, just a second. Make sure this is working. But I have been in the Army for the last 17 years, 4 years at West Point before that. And the only reason I bring that up is it's going to help set the scene for this story. Otherwise, this story may not make much sense. In 2011, I was leading a Joint Special Operations Strike Force in Logar Province, Afghanistan, on a night raid. During that night raid, these 3 individuals were severely wounded with enemy fragmentation grenades, as well as enemy small arms fire. Everyone in the trauma field is familiar with this principle called the golden hour. And so basically, as soon as that incident occurred, the clock started counting. We had 1 hour during which we need to get them medical care as soon as possible if we're going to increase their chances of survival. Luckily for them, the unit was extremely well-trained and had a lot of combat experience. So within 30 minutes of the first grenade going off, the fight was ended. All the casualties were packaged. We had Nextfill HLZ secured, and they were on a helicopter moving out. Despite that, 50 minutes after the first grenade went off, Oscar Zepeda in the top left corner got to the surgeons with tourniquets on all 4 limbs and no discernible pulse. Luckily for all of them, they made it in under an hour. They got surgical care. They're all still alive today. Most people aren't that lucky, or a lot of people are not that lucky. So the World Health Organization estimates that about 4 million people die every year due to uncontrolled bleeding events, massive traumas. So my research in the PUN lab in the emergency medicine space, we're trying to expand that golden hour out through the development of novel polymer-based hemostatic agents. So now let's talk a little bit about hemostasis. I'm sorry, the slide titles, I need to move that. I'm not going to be able to. My apologies. Hemostasis basically is your body's natural mechanism to reduce and stop blood loss. It starts with some type of an insult or injury, and then moves into a 4-step process, with the first step being vascular spasm. Basically, the smooth muscles constrict to reduce blood flow and blood loss. Next, you have primary hemostasis, where the platelets are activated via the release of von Willebrand's factor, and they stick to the exposed collagen in the extracellular matrix. From there, these platelets release thromboxane A2 and ADP, activating other platelets, which aggregate and form the platelet plug. The next step is secondary hemostasis, which is your coagulation cascade and the formation of the fibrin network through the intrinsic and extrinsic pathways. Finally, we have clot retraction and fibrinolysis, where tissue plasminogen activator, enzymatically activates plasminogen to plasmin, which enzymatically digests the fibrin mesh network. Trauma complicates this. So when you're in class 3 or class 4 hemorrhagic shock, you've lost 30 to 40% of your total blood volume. The lethal triad begins to become a problem. Basically, it's a metabolic failure that continues to spiral downhill. So hyperthermia leads to a decrease in metabolism, which increases acid, leading to lactic acidosis, which reduces thrombin generation, platelet activity. All of this leads to coagulopathies. The two that we'll focus, or we'll look at first, the glycocalyx. So along the endothelial cells, you have this glycoproteins and glycolipids that prevent vascular leakage. But when you have hemorrhagic shock, that glycocalyx is shed, and so now you have vascular leakage, compounding these issues, further driving blood pressure down. Another leading cause of death due to coagulopathies is hyperfibrinolysis. And so this is where even if your blood can clot, you have so much plasmin in the system that they rapidly digest those clots, and the blood keeps leaving the body. So how do we clinically diagnose hyperfibrinolysis? We use rotational thromboelastometry, powerful clinical viscoelastic tool. The way it works, on the left, you see that diagram. Basically, you have a small cup, you fill it with blood or plasmin. You have a rotating sensor pin in the middle of it. As the clot forms, it sticks to the sides of the cup and to the pin, and it resists the oscillation of the sensor pin. That reduction in oscillation is measured as a torque force, and the amplitude of the torque sine curve is plotted on the y-axis here as clot amplitude or clot firmness in millimeters. Some key metrics you can get from this plot are maximum clot firmness and fibrinolysis. So the drop as this curve comes down, the difference between maximum clot firmness and the new value is your clot lysis from fibrinolysis. So what does hyperfibrinolysis look like in a ROTEM output? It is this drop here. This APTEM study puts aprotein in with the blood clot, which inhibits fibrinolysis. And so you can control and prevent fibrinolysis, and you'll see a plot more like that. So what else inhibits fibrinolysis? Factor 13 naturally in your blood cross-links the fibrin network, resulting in a denser clot that's more resistant to fibrinolysis naturally. So this, in our group, the last 10 years, starting with Dr. Leslie Chan, moving all the way down to the 5th generation myself, has been working on polystat, which is a hemostatic agent that attempts to mimic factor 13. So factor 13 covalently cross-links the fibrin network. Our polystat doesn't do that. It reinforces the fibrin network through hydrostatic interactions. Basically, what it is a methacrylate polymer backbone conjugated to the fibrin with fibrin binding peptides that facilitate those interactions. And we'll show you here in just a second how that works in the fibrin network. But first, in ROTEM, you can see how polystat inhibits that fibrinolysis, right? So in the negative control, we have that drop from maximum clot firmness. In other words, fibrinolysis happening. You put polystat into the clot and you don't see that effect. So Trey, another researcher in the group in the polystat space, has studied this for quite a few years now. And he was looking at polystat's effect in traumatic animal models. And he noticed an odd artifact. So I just showed you that polystat inhibits fibrinolysis. He started observing several years into his own work that it was now not doing that for whatever reason. And so the first thought that he had was, okay, well, let's inhibit fibrinolysis and see if I still see this odd artifact. And it's still there. So he added the aprotein to inhibit fibrinolysis. He still observes some form of a drop on the right side of the graph. This could be interpreted as clot softening or clot contraction. He wasn't sure. So a major factor in clot contraction is the platelets. So he removed the platelets and just ran platelet poor plasma. And sure enough, the artifact disappears. And you notice that they all form about the same maximum clot firmness with no decrease on the right-hand side. Now, if you're not familiar with ROTEM, you might look at these and say, hey, what about this pink bar that's changing pretty dramatically through these tests? All that is the software for this instrument. It doesn't change the color on the output unless the maximum clot firmness exceeds a set 22 millimeter threshold. And so what you can really tell by this pink is the rate at which the clot is being formed. And you can see that polystat seems to be forming the clot faster. And we're going to come back to that in just a second. But the artifact is gone. He started to look into the literature a little more and finally realized what several of you already know, which is that as the clot contracts, if it contracts too much, it pulls the blood away from the cup and the signal drops because there's no more resistance now. It's only blood clot stuck to the sensor pin, freely rotating because it's not stuck to the edges of the cup anymore. So it was a kind of an artifact that was synthetic. It's not actually indicating any type of clot softening. What it is showing is that polystat increases clot contraction, which kind of leads to most of my work. You can visually see it right here in the Eppendorf as it pulls away from the Eppendorf sides as the clot contracts. But that was all animal models. So the next question was, is it in human blood as well? And that's where my work began. So I adapted a method from the Weissel group that utilizes FITC BSA or FITC albumin and fluorescence to measure clot contraction. But generally how this works is you carefully paint the inner walls of these wells with a dilute solution of Triton X, which is just a lubricant. And then you add the blood in. And if you're careful and you don't paint the bottom of the well, then the blood clot will stick to the bottom of the well. It will contract and it'll push the FITC that you dosed it with out. And as that contraction occurs and it goes more and more, as the contraction increases, you'll get an increased concentration of FITC, which will show up as an increased fluorescence intensity. So after much tinkering, we finally got this working. And we sure enough saw statistical significance in terms of fluorescence intensity and thus clot contraction between polystat treated whole human blood and a control polyscram human blood across 5 donors. Trey then looked at axial force, so the force that the platelets were applying to the clot. So in rheometry, when you put a sample on the instrument, you have to specify the gap height very specifically to single micrometer level. But the sample is going to contract or expand depending on what you're studying. And so most of these instruments will apply an axial force in the negative, which is the up direction, or a positive down direction to compensate for that, to maintain a gap height. Because if the gap height changes, then your strain values are going to be off and it's going to screw up all of the results. So we used this, and across 7 human donors, he normalized for the force per platelet using complete blood counts and found an increase in polystat force generation per platelet as well as rate of force generation. So where does that leave us? We know that polystat increases clot contraction and it increases the platelet contraction forces in humans and animals. Platelets have to be involved. So that leads to our hypothesis that polystat increases clot contraction via 2 overlapping mechanisms. The first is what we call mechanical transduction. What we mean by that is polystat is reinforcing the microstructure of the fibrin network in such a way that when the platelets pull on the microstructure, the reinforced microstructure can redistribute and translate that force across the entire mesh network rather than it yielding in those places prematurely. The next effect, and this is pretty well documented, that platelets will pull harder on a stiffer substrate. So if polystat reinforces the fibrin network, makes it stiffer, increases its elastic modulus, it should result in a stronger pull, a larger force generation per platelet, which is what Trey had found previously. But to really test these, we need to be able to look into the microstructure. And that's where we leave ROTEM and we transition to the field of rheology, which is where I have a little background, spending 3 years doing blood hemorrheology at West Point. ROTEM, powerful clinical tool. It fails, though, when you want to look at the entire strain range, because it only looks at a very narrow in the linear viscoelastic range. Rheology, on the other hand, looks at the entire strain regime, linear and nonlinear. Before we go a little bit further into rheology, I wanted to just make sure we set the groundwork on fibrin and the structure of the fibrin mesh network. So through thrombin proteolysis, fibrinogen is cleaved into the fibrin monomer. And then you have these knobs and holes, A knobs and B knobs. Those interact to form a double-stranded fibrin oligomer that we call a protofibril. You'll see a crude drawing over here that I did. And the reason that matters is you're going to see those more as we go. So when you see this, think protofibril. Then you've got these dangling items here, which are the alpha C domains. Those alpha C domains, through lateral aggregation, interact, and those protofibrils form a protofibril bundle. My very detailed drawing would be here. Those bundles form a fibrin fiber, which then has branches and nodes, and that forms the overall network, the mesh network. ROTEM allows us to see the bulk properties, viscoelastic properties of that. It's been well published in literature, though. If you want to know the forces and the changes at the microstructural level of interprotofibril sliding or intraprotofibril stretching, you need to look in the nonlinear viscoelastic range, specifically between 10 to 100% or even beyond strain amplitude. And that's where rheology takes over. So how does rheology do this? Generally, you have a stationary plate with a sample on it. A mobile plate comes down on top. You apply a strain through angular displacement, which appears as a sine curve, and you get a stress sine curve response. In the linear viscoelastic range, it should look like this. The shift is delta, or your phase angle, and this is a quantifiable metric of how viscous or how elastic your viscoelastic material is. All right, so back to the experimental design to answer that hypothesis. We wanted to start with a purified fibrinogen system to eliminate platelets. And the other major difference that we wanted to look at, most rheological studies for fibrin networks, fibrin gels, and blood clots, look at it after the gel is fully formed. So we're looking in terms of several hours after to even 24, 48 hours afterwards. But we had seen that polystat seems to be impacting the very initial stages of clot formation and fibrin network formation. So we wanted to look in the first 10 minutes approximately. To do this, I dropped the frequency down, but still maintained a pretty broad strain amplitude range. The output you get looks something like this. The y-axis is in pascals, x-axis is in strain percent, and it's both log scale. The green curve on top is your storage modulus. The blue curve is your loss modulus. And all we can really tell from this output is intercycle changes. So each one of these data points has underlying it 500, 600, 1,000 data points throughout the entire oscillatory cycle. And then this is the average output. You'll notice also we've got a linear range, strain stiffening, peak, and then strain softening as we approach the nonlinear range. I'm going to talk briefly about the limitations of the instrument that I used, and we can discuss this more in the closed door session if the committee wants to. But suffice it to say, the DHR3 stress-controlled instrument is a little bit of a sledgehammer, as opposed to a nice, fine, precise instrument that might cost, several orders of magnitude more. But it can still do what we need it to do for the most part. Where it fails is in the very high strain regime and the very low strain regime. And it's not because this instrument can't function there. It can. It just starts to fail when we're looking at delicate biopolymers. The good news, we already have seen that between 1% and 100% strain, That's where we need to look to see the microstructural differences in the fiber network. And if you look at physiologically relevant shear rates in trauma models, you'll see that those strains are appropriate as well. So we're going to be able to use this instrument to see the space that we need to see in terms of strain amplitude. All right, so just looking at the average values across the three strain amplitudes here. So underlying this, we've got sample size of 12 for each clot type. On the y-axis, you've got your storage modulus in Pascal, and on the x-axis, you have oscillation strain percent. The dark gray bar on the far right is polystat, and then you have your two controls on the left. You'll notice that polystat produces larger storage modulus, so your elastic modulus is larger across all three amplitudes, but it's not statistically significant until we get to that 100% strain range. Looking at loss modulus or your viscous modulus, you see the same increase in polystat here. So polystat seems to be making the fiber network more elastic, and it's better able to viscously dissipate forces that, in other words, translate those forces across the network. The significance, statistically speaking, appears to increase as we get closer to 100% as well. So what do we think is happening? Well, we think that polystat, based off of its radius of gyration and a lot of the work that's already been done on polystat, is reinforcing those alpha C domain interprotofibril sliding, inhibiting interprotofibril sliding, resulting in a stiffer, more resilient microstructure. We're about to dive into this 100% strain and look intra-cycle what is happening. But before we do that, let's just talk a little bit about the transition to nonlinear rheology. So we originally had that purple curve for our linear. Now we're going to distort that curve. It's still shifted by some delta or phase angle, but now it's distorted. And so how do we interpret that? Usually it requires a lot of math, and there's also a lot of different ways to do this in the rheological community, with disagreement over what is better and which is more effective. The big challenge, what we're really trying to do at the end of the day, is we want to take this distorted curve and we want to translate it back to physical meaning in terms of the microstructural changes taking place in the fiber network. Mathematically, some of the ways you do that is you break this apart and rebuild it in terms of a series expansion, whether that's Chebyshev polynomials or a Fourier series, and then you can further do Fourier transforms to develop the harmonics and look at harmonic ratios. From this, you can say if the third harmonic ratio versus the first is positive, then you're in a strain stiffening regime. If it's negative, it's a strain softening regime. But we want to go even deeper than that. And so I'm utilizing something called the series of physical processes. And you can think of this in terms of analog versus digital a little bit. This is a newer method. It's gaining a lot more traction in the last 10 years. Traditional Laus interpretations, all those mathematical processes that I suggested, generally give you this map and compass approach, whereas the series of physical processes framework, which was developed by Simon Rogers out of the University of Illinois, it basically gives you a real-time information on where you are and what is happening, how it's changing. Mathematically, how do you do this? You use something called the Freinet-Serret or tangential, normal, and binormal approach, differential geometry. You take your stress, strain, and strain rate, and you project it in 3D deformation space. And then you describe every single point along that curve as a series of vectors, the tangent, normal, and binormal vector that you see represented in the purple. From there, you can now describe mathematically instantaneous loss and storage moduli, as well as instantaneous phase angle, which means we can then transition to Kolkol plots. We can look at phase angle velocity, which is a metric of yielding and reforming and restructuring. And we can now really start to say what is changing and happening at the microstructural level. In case you're unfamiliar with Kolkol plots, I've got a little diagram here and down here. This is generally how you interpret a Kolkol plot. It's a projection on the y-axis of your loss modulus, x-axis of your storage modulus. You'll have this dashed line coming out of the origin. that is basically G prime equals G double prime. And as you transition from the elastic side to the viscous side, you're fluidizing. And as you cross back over, you're reforming, restructuring. Remember the phase angle. So the phase angle was that shift in the sine curves, right? Another way to look at that is to look at the complex modulus, which is described as the vector from the origin to any point on that Kolkol plot. As it traces that Kolkol plot, this phase angle from y equals 0 up to that vector changes. So we take the derivative of it and we can see how the phase angle is changing over time. And that's what you're going to see over here. That is the degree of yielding and restructuring, reforming that's occurring. If it's positive, it's yielding. If it's negative, it's restructuring and reforming. And this has been utilized quite a bit by followers of the SPP method. Why is it valuable, especially in terms of biopolymers? Most traditional methods look at yielding in terms of yielding at a single critical stress. There's a lot of ways to describe yielding in Laos, but most of them are that single critical stress yield point, whereas SPP allows us to look at it as a process. So on the Kolkol plots, you always start over here. At first it's thinning, then it strains stiffening. And so that's kind of the point we want to emphasize because it was one of the main differences we'll see with polystat. And then you start to soften and then thin again. You'll notice the phase angle velocity. We've got the yielding portion up here, and we've got this more significant negative portion down there. So that's about what they look like. So back to the N equals 12 runs of purified fibrin systems projected here. On the left, you have a negative control. In the middle, you have a polyscram control. And on the right, you have polystat, all at 100% strain amplitude. So now we're intracycle. We're just looking what's happening in that average single data point that we looked at on the bar graphs. The biggest difference here, these are also overlaid with phase angle. So color-coded, black means it's more solid, blue means it's more, red means it's more liquid-like. The biggest difference is in the polystat clots, we have a much more dramatic strain stiffening response. In terms of phase angle velocity, we've got the yielding is positive and the restructuring reforming is negative. So we started to look at the means. So the way you do this statistically is you go through and you just average out the peak values in terms of the positive side and then again in terms of the negative side. And we just wanted to look and see if there was a difference. Turns out there's not. So polystat is not inhibiting yielding of the clots. The reason I think that this is happening is because I don't think we've taken it to a high enough strain amplitude. I did run this much beyond 100%, but due to the limitations we can discuss later, what happens is the strain amplitudes it actually records at jump so dramatically in between iterations that it's not consistent enough to really determine anything out of. But what's really interesting is the reforming. So when we look at the mean values for reforming, we now see statistical significance. So polystat is dramatically improving the microstructure's ability to reform and restructure under deformation at high strain amplitudes. Back to the microstructure. The combination of the increase in elastic and viscous modulus combined with that increased reforming restructuring leads me to believe that polystat is not only helping with these alpha C domains, but also intraprotofibril in the knob and hole interactions, reinforcing those as well. So back to the clot contraction. What we think is really happening now, based off of all that, is that the polystat allows the platelets to pull harder on the stiffer substrate. And as they do that, polystat allows the fibrin mesh network to distribute and translate that force across the entire network broadly. Net effect, greater clot contraction, stronger, stiffer, more resilient clots. In summary, I'll be finishing up this manuscript. It's been through a couple of drafts already. It's pretty much close to done, and I'll be a co-first author on that. Methods paper. So each one of those 12, n equals 12 data points, when I started out, took about 8 hours, not including the actual running of it, because the data processing for SPP is extremely tedious and onerous, and it's large data sets. And so after wasting too many weeks doing that, I eventually developed a Python code to take the output directly from the instrument, clean it automatically, and process it through SPP. So it took 8 hours worth of work and turned it into the click of a button. And I think that this is could impact and help a lot of other people in the radiological community. So I'm going to use that and turn that into a methods manuscript that I've outlined already. I've collected a bunch of blood rheology work across multiple species. None of it has been statistically significant yet with polystat. But we know that polystat's been extremely effective in rats, but it's struggled in swine. We know there's physiological differences between the two, but we don't fully understand why polystat is failing. Is it a model issue? Is it the swine themselves, or maybe the actual bleeding model, trauma model? And so I'm looking at doing a paper based off of that. I just need to collect a lot more samples. In the future, I want to develop a machine learning algorithm to fully analyze louse. And so anybody that's played around with any of the new AIs out there, they can pick up on these little differences so much better than humans can. And I have a large data set that I can use for training, or at least seeding a synthetic data set. I think that I can develop a tool for that. I'm also going to be going back and doing more chemistry again in moles, building on the polystat that I developed at the beginning when I first showed up here. All of my stuff was built off of the polystat that I synthesized. But we're going to be working on low volume resuscitants now. So leveraging the oncotic effect, we're going to develop some polymers that do that. And then testing the new hemostat, so polystat 2.0 and beyond, with this rheology tool set that I've developed. I'd like to thank everyone in the lab. There's no way I could have done any of this in the last 7 months if it hadn't been for many of you, especially Trey pulling me along, and Shu and constantly drawing blood for me, and everyone donating blood, and all the help that I've gotten from everyone. So thank you for that. References and your questions before we transition.
Good for you, Trevor.
Any questions from the audience? We have time for maybe 1 or 2 questions.
Okay, I'll ask my standard question, which I ask always when this project is presented. How do you resolve?
How do you dissolve the clot afterwards?
Yeah.
You could add TPA to it, tissue plasminogen activator. You mean how do I dissolve it to clean it off the instrument?
No. Like you can't clean with the cloth. Like real life, you have a cloth.
Yes. Yes.
So is there a mechanism in your idea of how you're going to do that?
You mean if we make a stronger clot, how do we then go back and digest it? I mean, the short answer from my understanding is you could locally treat it with a large concentration of an antifibrinolytic like TPA or synthetic TPA. But beyond that, I'm not sure.
Okay, it looks like you're free to move on to the next section.
Outstanding. Hope you guys like space.
Also, Trevor, I think if you click hide meeting, that might,
Is that how it
might
would solve that?
potentially.
Let me do that.
I wish I could. That's pretty impressive.
It's under more, and then it should be like hide meeting controls. I think the one below it, yeah. Loading meeting controls.
Thank you all. You guys
Thank
are
you,
amazing.
Trevor. Bye-bye.
And it's back. Oh man. Look away. All right. So this next talk is about a grant proposal that I developed titled Factor 12 Inhibition as a Novel Solution to Thrombosis Prevention for Astronauts. And this thing's not working again.
I know. It's so amazing.
Please mute your microphones. Just mute mine. All right. So a little background. In 2019, a paper came out talking about something that had been discovered about a year prior. And so what was discovered during a routine ultrasound on the International Space Station was a thrombus in the interjugular vein of one of the astronauts. Now, obviously, this is a critical medical emergency on board a space station. And so lots of people responded, and they had them look at every one of the 11 astronauts on board. They found another partial thrombus in the interjugular vein of a different astronaut. They looked at blood flow patterns in the interjugular vein and discovered that flow rates had been reduced dramatically, and in some cases gone stagnant, and in others reversed flow. Stagnant blood can lead to blood clot formation. Prior to this, no one had ever recognized clots in astronauts in space across approximately 700 astronauts that have been to space to date. There was a working group that met just last fall. Results were released about 3 weeks ago with NASA and the European Space Agency. This is a diagram from that working group where they show the increased cross-sectional area and the reduced flow rate that was discovered averaged across all 11 crew members. And this is where they found the thrombi in the 2 crew members. Obviously problematic. So what's leading to this? What's causing it? When you go into space, microgravity causes a cephalid fluid shift, which means that most of the fluid in your body shifts in towards the upper half of your body. This has dramatic effects on your cardiovascular system. So as that fluid shifts into the upper half of your body, the baroreceptors, pressure receptors in your body, recognize a fluid overload, and they cause your body to urinate heavily and reduce thirst. This drives total blood volume down. You also have systemic vasodilation occur as a cause of microgravity, and that reduces your systemic vasorestriction, which further drives that blood pressure in terms of mean arterial, systolic, and diastolic blood pressures all down. Net effect, you experience anemia, hypovolemia. The blood vessels in your legs begin to constrict because they're used to having an increased pressure relative to where they are now. And you also have an increase in oxidative stress leading to endothelial dysfunction, which we're going to talk about more in a second, but that can lead to arterial stiffness. Long term, this has major implications to your heart. As the blood volume goes down, the workload goes down, which means the muscle mass decreases and your heart literally shrinks. Inside the vascular lumen, these are endothelial cells. And this is kind of a comprehensive look at some of the microgravity-induced changes. You have cytoskeletal rearrangement that leads to endothelial dysfunction. You have an increase in clotting factors building up due to that endothelial dysfunction. You have apoptosis pathways that are activated and an increase in reactive oxygen species. And then when you combine reduced flow rates, you have platelet aggregation. All of this impacts Virchow's triad. Virchow's triad is how we describe risk of clot formation or thrombus formation, hypercoagulability, blood flow disturbance, and vessel injury. All of these are a factor. I didn't mention the vessel injury as much, but you saw the increase in cross-sectional area in the interjugular veins. That was due to the cephalid fluid shift. And that results in vessel injury to those veins and endothelial dysfunction as well. So what is the current gold standard? This comes out of this research working group that just met. Basically, they had 4 different solutions that they proposed. 3 of them are mechanical constriction, basically, mechanical devices. And the main one that they focused on was the need to study extremely low dose usage of current anticoagulants, like direct oral anticoagulants, and or find new ones. Because the biggest issue, and we're going to talk about this in more detail in a second, is the risk of a bleeding event. So anybody that's had a relative or has personally taken low-dose aspirin to thin their blood because they're at risk of developing a thrombus knows that there is a small risk of a bleeding event. That risk is manageable on Earth, but 6 months into a mission to Mars, that is untenable. How did they solve this for the astronaut in space? They put her first on low molecular weight heparin for a few days. Eventually, it reduced the clot. They did a bunch of studies to make sure that the clot had been reduced enough. And then they put her on a direct oral anticoagulant, specifically apixaban, for the next 2 months while she was in space. They ceased that about 4 days prior to reentry because reentry is rather aggressive. And they didn't want her to start bleeding out during that. And she was fine. So getting back to antithrombotic pharmacological interventions and their risk of a bleeding event. We already highlighted how this is untenable in space, but let's look at this list on the left, which is by mechanism, holistic in terms of what's out there right now. On the right, you've got your coagulation cascade, and we'll kind of jump back and forth here. We'll start out at the top. Broadly, what you're looking at is you can target antiplatelets. You can go after the coagulation cascade. You can target vitamin K, or you can go after thrombolytics. Okay. Generally, the risk of a bleeding event sort of increases as you go down with some variances. You can see the numbers all right here. Antiplatelet drugs generally work by inhibiting receptors on the surface of platelets. So think P2Y12 receptors or your glycoprotein 2B3A receptors. Aspirin fits in this as well. It inhibits the production of thromboxane A2 through inhibiting the COX enzyme. As we go down to anticoagulants, you now have your direct oral anticoagulants. So these are what you can usually take outside of the hospital setting. And these are generally targeting factor 10. You also have factor 2 inhibitors targeting thrombin. And then you get into your direct antithrombin 3, which targets basically a combination of factor 10 and 2. This is heparin. So this has a pretty high bleeding risk. And so this is usually an inpatient style treatment. Vitamin K, if you look everywhere on this coagulation cascade where you see an E, all of those factors require vitamin K. So if you inhibit vitamin K production, you stop the coagulation cascade from functioning. So warfarin does this. Thrombolytics, they go after breaking up that clot, busting up the clot via an increase in tissue plasminogen activator. These are usually locally done because they have a pretty high bleeding risk. So what we want to find is something that reduces the risk of a thrombus formation. So something along these line of thought here, but doesn't increase the risk of bleeding, right? Because even 1% is too high in space right now. So what I'm suggesting is looking way up here. And everybody that's looked at different cascades in complex biological systems knows that starting at the top of the cascade is risky. I agree. In this case, I think it's manageable, and there's examples in nature of why I think that. The first reason is that factor 11 can be activated with thrombin, so it doesn't even need factor 12. In fact, in some of the new medical textbooks, there's something called the cell model of coagulation, which actually eliminates factor 12 entirely. As far as examples from nature, if you look at whales and dolphins and birds, they lack factor 12. We believe this is some type of evolutionary shift. Factor 12 is activated generally with negatively charged particles like silica from dirt. So if you think a wound in an animal, usually exposed to dirt, initiates the intrinsic pathway. Whales are surrounded by water. Birds spend most of their time in the air. So we think this is some type of an evolutionary change, but they lack this factor. They're able to form, perform hemostasis just fine. And they generally demonstrate a decreased risk of forming thrombus in vivo. There's humans with genetic mutations. In fact, that's how Higman factor or factor 12 was first discovered, was a genetic mutation that inhibits factor 12 production. There's several drugs actually that are targeting factor 12 inhibition as treatments for genetic blood disorders. Several of them are already through clinical trials, specifically for hereditary angioedema. The studies that led to those clinical trials were in vivo genetic knockouts in rodents and non-human primates. They showed a decrease in thrombus formation and no increase in bleeding. But no one has looked at factor 12 inhibition as a treatment or preventative strategy for astronauts. There's quite a gap in the scientific literature for a couple of reasons. One, we didn't realize this was an issue until about 5 years ago. And two, it's very difficult to measure mechanical forces on blood clots that are formed in microgravity. Just looking at a broad search of microgravity in blood, you'll get thousands of returns. Google Scholar, kind of the same thing, increase the numbers a bit. As you narrow this search down, you look at microgravity and thrombosis, or microgravity in clots, or blood clots in microgravity, or simulated microgravity, the numbers just crash. You're looking at like 30 to 50, depending on the search engine you're using, and almost all of them are in the last 5 years. And honestly, this title of this paper really kind of summed it up. Has a serious problem been overlooked for more than half a century across 700 astronauts in space? And as you really apply some type of a microstructure or mechanical understanding to clots that are formed in microgravity, the numbers of papers are zero. If you want to look at factor 12 inhibition to clots in space or microgravity or simulated microgravity, also zero. So that's part of the innovative aspect of this study. The other innovative aspect would be to utilize clinostats, which we'll talk about more in a minute, to simulate microgravity and then measure and study how the clots are formed in microgravity and how that clot changes or is not formed as a result of factor 12 inhibition. The specific hypothesis is that factor 12 inhibitors will reduce mechanical strength of blood clots that are formed and reduce microgravity thrombosis formation. AIM-1 is going to focus on measuring the mechanical properties using the rheology toolset that I already showed you in the previous presentation on blood clots formed in a simulated microgravity environment using several different instigators and then also inhibiting factor 12. AIM-2 is going to look at dynamic clot formation, both in normal gravity and then putting that into a clinostat and watching it in a microfluidic device and watching how the clot forms or doesn't form when we apply a factor 12 inhibitor. AIM-1. So clinostats. In the top left corner, you have an example clinostat. Excuse me. Basically, how this works is like a gyroscope. It rotates around several axes in such a way and at such a rate that it can average out the vector of gravity to a very low level. Depending on the different algorithm you're using in terms of fast rotation or slow rotation, the number of axes that you apply, usually 1 to 3, you can get gravities as low as 10 to the -5th, which is effectively what astronauts experience on the International Space Station in low Earth orbit. For factor 12 inhibition, so the factor 12 inhibitors that are currently through clinical trials or working their way through clinical trials for these genetic blood disorders are mostly monoclonal antibodies. Rather than use one of those, I want to use corn trypsin inhibitor because it's the thing that most of those studies built on. It's very well characterized, it's cheap, it's easy to get, and there's lots of other literature looking at it in terms of clot inhibition and factor 12 inhibition. And then we're going to be applying confocal microscopy. So there are some clinostats that can have mounted microscopes on them, and we'll use different fluorescent tags to look at different parts of the clot, whether it's the platelets or the fibrin or the red blood cells, to really understand how the microstructure is changing visually and add that to the rheological understanding. The way I see it is a series of experiments. First, just starting with an epi with blood in it, so plastic epi to reduce the risk of initiating the intrinsic pathway accidentally. And then we'll put whole blood in there with and without the factor 12 inhibitor. And we're just going to run it in microgravity, and we're going to see if a clot forms or if it doesn't. If a clot forms, then we can start measuring mechanical properties, and we can start using confocal microscopy and those labeling techniques to really look at differences between factor 12 inhibited blood clots and the controls. Then the next step will be to start initiating the intrinsic pathway, starting with colloidal silica to initiate. And ideally, the factor 12 inhibited blood will not clot. If it does, we can then start looking at differences in the clots in terms of mechanical properties and microstructure. And finally, we're going to hit it with thrombin as an initiator, because thrombin will for sure clot it. As we said before, it can initiate factor 11. And so then we can measure differences in terms of clot strength. At the end of the day, for AIM-1, we expect to find a reduced elastic modulus in factor 12 inhibited blood clots, an increase in that metric of yielding, the phase angle velocity we looked at before, and we're going to gain microstructural insights in terms of blood clots formed in microgravity, which hasn't really been published in the literature yet. So that allows me to back up just a little bit too. So in the literature, it's not a complete gap. They have looked at red blood cells. They have looked at microfluidics in simulated microgravity before. What they haven't done is measured mechanical properties of any of these clots. And they haven't looked at clot formation in terms of microscopy in a clinostat. All they've really looked at is red blood cells and how they interact and respond to microgravity. Long-term implications: reduced risk of thromboembolism in astronauts with a reduced risk of bleeding events. For AIM-2, now we're going to add in microfluidics devices to look at dynamic clot formation. So think similar number of experiments, but now we're going to drop the flow rate to the low shear rates that they observed in the interjugular vein. We're going to run it at 1G, and then we're going to put that microfluidic device in a clinostat, and we're going to run it in simulated microgravity as well. And we're going to watch how long it takes for clot formation with the same progression of initiators. And we're also going to watch, how large the clot is. We can measure how large the clot is. And then finally, we're going to add in TPA and see how quickly fibrinolysis takes over to see if it is, in fact, a weaker clot, more susceptible to fibrinolysis. At the end of the day, we expect an increase in clot time for factor 12 inhibited clots, a reduction in clot area, and an increase in fibrinolysis, as well as microstructural insights gained through the visual observation of these dynamically formed clots. All right, so potential challenges. The first one up, and probably the biggest one, is access to a clinostat. These things cost $50,000 to $80,000. They're not cheap. And if you have the money, you can't get them. So there's very few suppliers of these things, which is bad. Usually there's a several-year backlog. This has spawned creativity in the research community. So there's several papers that show that you can build these things with 3D printing, and there's papers outlining how to do it for the range of $3,000 to $5,000. So that's one approach. I'm not real good at building things, so I have a different approach. Last week, I met with Yi Zhang. She's a senior scientist at the Microgravity Simulation Support Facility at the Kennedy Space Center. They have lots of these, and they're huge. They have mounted microscopes on them, and they're awesome. And she suggested a lot of different pathways through traditional, grant proposal routes through NASA. If you get funded through NASA, you can work at their facility for free, no problems. The biggest thing that she recommended, though, is they've brought other military personnel in before. And she just on the spot offered me the chance to just go there as an intern. The catch is I'd have to pay my own way. So I'll have to find some funding at some point just to pay for lodging. But basically, I could go there. I can use the clinostats there for free. So I think that this is a good solution to the clinostat problem, because I don't think we can buy one and get one in time. Signal to noise ratio. So I think as I look at this, one of the other big problems is whether or not we can make the clots form. So either they're going to form too fast, they're going to form across every control, or they're not going to form at all. And so we're going to have to play around with concentrations and probably even maybe the coating of the epi that we're going to put it in. The other thought that I kind of skipped over is I plan on trying to incubate it first in an epi in the clinostat, then removing it, dosing it with calcium and whatever initiator we want, and then putting it in basically like a 24-well plate with a rubber stopper, so that it's sealed and contained while it's in simulated microgravity. But I think that that's going to take some actual experimentation to see what works and what doesn't work. In terms of microfluidic flow issues, there is some good paper out there looking at microfluidic devices for blood clot formation in simulated microgravity. So the dynamic formation, not the mechanical studies. And so that I'm less worried about. That I think has already been they've worked through a lot of those problems, and I think we can build on those protocols for the factor 12 inhibition studies. This is kind of a proposed timeline breakdown. In conclusion, it's a critical need. So I didn't really talk about this. I alluded to it with the selection bias of healthy astronauts. So one of the reasons this hasn't been really discovered before is astronauts are chosen to be physically fit and at low risk for developing a thrombus. But if you look at the Scott Kelly twin study that NASA did, he spent 540 days in space across 5 different periods of time. And they compared him to his brother, an identical twin. He had significant health deleterious effects from that continuous 540 days in space in microgravity. And this was when he was protected by Earth's magnetic shell. When you leave that and you go to Mars, you're going to add in a significant radiation dose. He was already getting a chest ray, X-ray a day equivalent of radiation. You leave the protection of microgravity, you're going to have that as well. Radiation complicates the endothelial dysfunction as well. So all of this to say the trip to Mars is going to be really dangerous, obviously, to astronauts. If you start thinking about it in terms of space tourism, where we're no longer bringing people that are physically fit and healthy to space, this is going to go up, this risk. So it's a critical need. I believe that using factor 12 specifically for this use case is an innovative solution that hasn't been published before or looked into very much. I think that this study is comprehensive in terms of mechanical and microstructural design and analysis. And I think that the future impact could significantly improve the chances of a successful mission to Mars and beyond. I'd like to thank everyone in the group, and these are my sources pending your questions.
Okay, we have time for questions for this one. There's got to be some, right? Okay.
So you presented on polystat. We know it's great at targeting fibrin. Do you think polystat has a role in terms of helping better target clots and break them up for this proposal in your second half?
I mean, I suppose you could conjugate something to polystat to help with it, because it does target it. So it would be a delivery mechanism potentially to some type of, plasma derivative or small molecule that assists with that.
Do you think it'd be easy to test in your setup?
Easily. Yeah, for sure. Ethan.
Excellent job. Really enjoyed your talk.
Thanks.
I was just wondering what strategies you might have in mind for doing the actual inhibition of factor 12. You've convinced me that would be a great approach, but do you have any kind of therapeutic agent in mind?
Yeah. You mean other than using just CTI to study it?
I guess so.
So corn trypsin inhibitor has been broadly published as an effective factor 12 inhibitor, and they've got different dosing schedules to achieve different effects and everything. That's pretty widely published. So
Cool. Okay,
Yeah,
I didn't
no
realize
issues.
That was also
If you're talking about, what future, like development of future drugs, building on the monoclonal antibodies, and there is a patent out there already for an aptamer approach, which potentially we could look into.
awesome.
Yeah.
Thank you.
I have a question, sorry. Based on the blood studies that have been done, do you know how long it has to sit in the clinostat to develop some of these
Yeah.
complications? And do you think that's gonna be a problem? Just due to shelf life of blood?
Yeah. So the microgravity effects happen within the first couple of hours, 1 to 3 hours. So I think that will be okay due to shelf life issues. Totally valid though. And ideally, this is an in vivo study that is more advanced than the typical hind limb unloading in rodent models. Ideally, it's a rodent in a clinostat, and we're looking something in vivo like that. Because yeah, the blood, if you don't know blood, it basically after about 4 hours, its clotting efficacy degrades pretty rapidly. So yeah, good point. Yes.
So if you can make microgravity, can you recreate gravity? Or is it science fiction?
No, you can create gravity. I mean, the centrifuge, right?
No, I mean.
Oh, anti-gravity?
So, so that you have gravity actually in the space.
Yes. Okay. So great question. They have looked at this, right? So we not only is clotting an issue in microgravity, but more deleterious is the loss of muscle mass and bone density, which are really dramatic effects that take over within days to months of exposure to microgravity. So they've looked at, can we make a space shuttle or a space station that simulates microgravity through centrifugal force? The main limiting factor right now is the cost in terms of tonnage to space. So potentially, if SpaceX can keep driving that price down in terms of how much it costs to move a ton from Earth into outer space and put it into low Earth orbit, then that might become a reality. But right now, it's completely out of the realm of possible. We're orders of magnitude away from being able to do that right now. Yeah.
Okay,
know.
I think we're gonna have to stop and
Yeah.
move to the closed door session.
Okay.
Thank you.
Thank you
for
all.
joining.
Thank you. Let me just end the Zoom meeting. Thank you all for attending on Zoom.
Wait, here you are.